Accurately graph these graphs. So we have f of x equals 2x plus 2. We have a y-intercept of 2, slope of 2, rise 2, run 1, or down 2, left 1. Have our 3 points there. Graph it. We have g of x equals 1 half x minus 1, negative 1, and then up 1 over 2, up 1 over 2, or down 1 over 2 to the left. Graph y equals x, dotted line through. It's looking like that. What do you notice? Label 3 points on each graph. Okay, so I'm going to have this one, and this will be 0, 2. This one will be negative 1, 0. They both share that one, negative 2, negative 2. I could also use, oh, the line is, I wonder if it's my extra scale there. No, I didn't, when I graphed that, it was slightly off. It should be like there. That's better. And I'll erase the other one. Note, if you make a mistake, it's okay to fix it. That's why we write in pencil. And then there was another point here, 1, 4. Label some points over here. This is 2, 0. This one will be 0, negative 1. This was a shared point, and over here was 4, 1. What do you notice about these points? We have 1, 4, we have 4, 1. 0, 2, 2, 0, negative 1, 0, 0, negative 1, and this was the same. The x and y values are switched. These two graphs are a reflection about this line. So the graphs are a reflection about the line y equals x. The x and y values of one graph are switched for the other graph. Let's take a look at this next part. Find f of g of x. F of g is 1 half x minus 1. So we'll have 2 times 1 half x minus 1. Just use this. Make that look a little better. And then add 2 to it. So we get 2x, 2 times x, or just x, minus 2 plus 2, which gives us x. G of f of x will be g of 2x plus 2, so 1 half of 2x plus 2 minus 1, and we'll get x plus 1 minus 1 equals x. Look at that. What a coinkydink. Or I think not. Let's take a look. The whole idea of what I was trying to do in that problem is introduce this concept of inverse functions. Now, have you seen them before? We've actually talked about them before, this reflection about the line y equals x. We didn't call them inverse functions at that point, but this is what they are. Let's take a look at the definition. If f and g are inverse function, then f of g of x, that's what we just did here, equals x for every x in the domain of g of x. And g of f of x, that's this one, also equals x for every x in the domain of which function? Of f of x. Their graphs are, what are they? Reflections about the line y equals x. And what's true about the coordinates of the points? They are switched. When you see this, this is a notation that we're going to use for f inverse. And the way you read this is it says f inverse of x. It is not an exponent. Actually, I'll just write it like that. It is not the same thing as 1 over x. If you think about it, and you put, we had this f equals 2x plus 2. If you looked at the graph 1 over 2x plus 2, remember that would be a graph that looks like this. That's definitely not the inverse of a line. So reciprocal and inverse are different things here. All right, here's an example. F of 3 equals 5. So what's the coordinates of that point? That point is the x value is 3 and the y value is 5. And this is for f of x. Well, what is it for f inverse of x? Remember that x and y values are switched. That would be 5, 3. So what is f inverse of 5 equal? In other words, what's the y value of f inverse when x is 5? Well, that's this point. That's 3. Let's take a look at this. We have f of f inverse. So f inverse of 5 is 3. And what's f of 3? That's the original function. That's 5. Why? What does an inverse do to the function? It undoes everything that was just done to it. And when we get into class, I'll show you a physical example of what we're talking about. That since I'm not going to put a video up of me walking around here, I don't have that technology. Let's take a look at this. Graph f of x and its inverse. So we have, this is taking x squared and it's going to shift it down 2 units. So we're going to go down 2 units. If we set it equal to 0, we would have x squared equals 2. So x equals plus or minus root 2. And that's going to be about 1.4, negative 1.4. We could plug in a couple values like 1. We also, you recall when the beginning of the year when we talked about graphing, we could go over 1, up 1, over 1, up 3. And we have the symmetric points on the other side. So we have this parabola. And towards the end of the year, we'll really see why that over 1, up 1, and over 1, up 3, over 1, up 5 works. Now, what would it be if I graphed the inverse? I have all these points on my graph. I just labeled here for f of x. I have 0, negative 2, and I have plus or minus 1 and negative 1, and I have plus or minus 2, and that went with 2. So for f inverse, remember they're switched. So we'll have negative 2 comma 0, negative 1 comma plus or minus 1, and then 2 comma plus or minus 2. So if we plotted those, we have 0, negative 2, 0, negative 1, 1, negative 1, negative 1, 2, 2, 2, negative 2, and that graph looks like this. Now, is this inverse a function? So for the rest of the time, our book, every time we say find an inverse, what it's really going to ask, what that's really meaning is find an inverse function. not just a relation. So is this a function? No, it's not, because for at least one x value, there are two y values, and you could also think of that passing the vertical line test. So this inverse right now is not a function. Now my question for you is, what can we do to the original graph that would make the inverse a function? How can we restrict the original graph that would make this graph for every x where there's one y, or pass the vertical line test? We want to, right now, notice how even when I wrote this chart here, I put -1 and I put two different values for the y. I want to have it so there's just one value. I only want one of these for the original one. In other words, I want to cut off half of the graph. So if I restrict the graph, if we restrict f of x equals x squared minus 2 for x greater than or equal to 0, then if I took off this piece there, then when we graphed it, I would not have any of those negative values, so the negatives would be gone, and it would be a function. Now, do we have to restrict it to x greater than or equal to 0? No. There's nothing that forces us to do that. We can make it x less than 0 or less than or equal to 0 as well. And I'll show you both in what result it has on the graph. So what we're going to do is find the inverse of this function, because now that does have an inverse. Let's go through the process. What we'll do is set y equal to f of x. So we'll put y equals x squared minus 2. And you got to remember, we're restricting this to x greater than or equal to 0. Then what we're going to do is switch x and y. So we'll put x equals y squared minus 2. And then solve for y. So we'll move the 2 to the other side. X plus 2 equals y squared. Take the square root. What do we get when we take that square root? There's always our plus or minus. Now at this point, the positive represents that top half of the graph. The negative represents the bottom. Which one do I want and why? Well, let's go back and look at it. If we restrict the graph to x greater than or equal to 0, then what's that going to tell us about once we switch the x and y value? Well, this is going to make our y value for our inverse greater than or equal to 0. Since x and y are switched, the domain of my original function will become the range of the inverse function. So based on that, which one do we want? We want the positives. So we would say x plus 2. And then our last is to change y to f inverse of x. So we'll say f inverse of x equals the square root of x plus 2. Now let's take a quick look. What if it was f of x equals x squared minus 2 for x less than or equal to 0? When I get down to this stage here, instead of taking the positive, this would force my y values to be less than or equal to 0 when I write x equals y squared minus 2. And then it's the same work, but which one do I want? Do I want the positive or the negative? This time I don't want the positive, and I would want the negative. So for this example, it'd be f inverse of x equals negative of square root of x plus 2. How can you tell if the inverse will be a function? So what could we look at for the original equation that would say, yes, my inverse will be a function. Why didn't this original one pass is because when we had two different x values with the same y value. So when we switched x and y, that forced two different y values for the same x value. So how can you tell if it's going to be a function? There's a couple ways you will see described. You can say it must pass the horizontal line test. In other words, the horizontal line test is saying for every y, there is one x. So a function that passes the horizontal line test is called 1, 2, 1. And what that means is it's a function. And what does the function mean? For every x, there is one y. And it's also the inverse is going to be it, or it passes the horizontal, and that's for every y, there is one x. That's why it's called 1 to 1. So in order to tell if the inverse is going to be a function, then it needs to pass either the horizontal line test or it needs to be 1 to 1. Now the function itself will be a function. For every x there's going to be one y. You just need to make sure that for every y there's one x. Give an example of a graph that will have an inverse. We're not restricted here. What I'd like to do is just make up one. I'll give one here. It could be a simple cubic graph. This could be a cubic or a fifth degree. Give an example of a graph that won't have an inverse. How about for right now, I'll do a cubic graph as well. What about a cubic graph that looks like this? That will not have an inverse. It does not pass the horizontal line test. It's not a 1 to 1 function. Over here, you could give an example of a line. You could give a square root function. You could give half of a parabola like we did in the previous problem. And then here, any even function that doesn't have a restricted domain won't have an inverse as well. And that's enough for inverses right now.